We now expand the ideas we used to develop the mouse core to develop a different core, which we're going to call a ghost core. It's also a video core, but it will display a game character, a ghost character basically, from the Pac-Man game. So the reason why we're developing a different core right now is because I want to show you a couple new things you can do with these sprites, which is animation and color. So let's get started with animation. So animation is usually generated by displaying different pixels one after the other, one after the other, one after the other. This can be done by just storing a bunch of pictures for the same character in different positions. So for example, here I'm showing you the same ghost character, but it actually has different positions. So I have 1, 2, 3, and 4. And the most obvious way, it's actually just moving its eyes, and not only this, it's also moving the skirt. So you're going to see that the first one is a little bit different than the second one, and so forth. So when you actually display these different sprites to one after the other sequentially with a specific speed, let's say 6 to 10 hertz, you'll have the notion of motion, basically, or an illusion of motion. Our eyes will think that that particular ghost character is actually moving. So in this core, we're going to expand the ideas that we use for the mouse core and generate this type of animation. And there's a name for these set of characters that we have in here. We usually call it a sprite sheet. And that sprite sheet can be stored either in the processor memory, which is the easiest. So you can take the mouse pointer, the same exact mouse pointer core that we stored, and then you can store this particular sprite sheet in the processor memory. And then whenever you want to display something new, basically you want to change it goes from this to this, you just go to the processor memory, it's not the core memory, and you send it to the core, and the core, basically you overwrite the RAM within that core, and you do this at very specific rates, and you can create this particular animation or motion. However, this is a little bit on the tedious because now your processor will be busy figuring out when to send and to read its memory, and there's like a lot of hassle in here. So we're going to develop a little bit of a better approach, and that approach is actually we're going to store that sprite sheet within the internal RAM of the core, and then the processor, all it needs to do is just basically indicate which one of these 4 images it wants to show, and that's about it. So the processor can actually display one of them, and internally also we're going to add another circuit that generates this motion basically by just automatically iterating between the different sprites within a sprite sheet. But before jumping into the details of how we actually implement this animation circuit, I also want to talk about a little bit about color. So in here we actually see the sprite sheet, and it's actually displaying just a very limited number of colors. Specifically in computer graphics, we use the term palette, and that palette tells me the set of characters that can be simultaneously displayed. In our case, because we have 12 bits, you can calculate the number of colors you can show, which is generally 2 to the power 12, let's say 4,000 colors. However, if I take a look at this particular sprite sheet, I don't see 4,000 colors. All I see is a really limited number of colors, specifically 4. So it turns out it's a little bit more efficient not to store the color itself, but to store some sort of a code. So we're going to encode these colors. So let me give you an example in here. So we're going to take a look at this particular sprite sheet, and I do see 4 things. And the first one is basically those one here, which are exactly black, which we call it the chroma key, the one that will basically blend. So whenever whenever we send this into the core, it will just basically take the background color and just place it in there. And that's basically what we have in here. The chroma key is exactly black. And now next we can take a look at the eye, and the eye here, I mean, they look a little bit bluish on my screen, but really this is actually the value 111 in hex, which is basically just a very dark gray, and that's basically that portion of the eye. I also have the particular red here. Okay, the body basically is red, and I can just say that's the body. And also I have the white portion of the eye, and that's basically the color. So if you see it, if you think about it, I only have 4 distinct colors. So instead of using 12 bits for each one of these colors, what I'm going to do is I'm going to encode them. And specifically, I'm encoding what they mean, what these colors mean. So I'm encoding that I need chroma key, I need that dark portion of the eye, and I need the body, and I need the white portion of the eye. So specifically, I was able to actually encode each one of these pixels, for example, in 2 bits only. So I have 4 colors, so I need at least 2 bits. So now instead of storing the whole 12 bits to store a bunch of zeros and a whole 12 bits just to store red or white, I can just basically store these two. And that's what we're going to be doing next. So shortly you're going to see that the RAM that we're going to be using, it will be storing 2 bits, but I'll take these 2 bits and then I'm going to put them through a palette coding circuit. And what that palette coding circuit it will just be a lookup table, maybe a ROM or even a combinational circuit because it's really small. And all it will do is just basically tell me, okay, well, you're outputting 0, 0. That means the real output should be 0, 0, 0 in hex. Okay, so for example, let's assume that the pixel value that you're reading is actually just 1, 0. So that coding circuit will actually really give you an output that is 12 bits in here, and that basically will be 0 xf00, 0, and that's basically the body. So in the code that we're going to see shortly, I'm going to have like some sort of a palette coding circuit. So this will allow me to code the color. So why would I need to code the color though? Well, it's a lot more efficient to store in RAM, and it'll also allow me to dynamically change the color. So let's talk a little bit about the efficiency of storing coded palettes as opposed to storing the colors, like the raw 12-bit colors. So if we have one image, kind of like what we did in the mouse sprite, let's in the ghost case, it's 16 by 16, okay, and since 16 by 16 are already multiple of 2s, I don't need to expand them. So what I really need is I need, for the 16, I need 2 to the power 4, for the other 16, I need 2 to the power 4, so technically I need 2 to the power 8 times 12, and that's basically 12 bits because I'm coding every pixel by 12. That's the number of bits. Like if you multiply these two numbers, you get the number of bits to code this one image. However, what I have is I have a sprite sheet, and on that sprite sheet basically have 4 image. So what I need to do is I also need to multiply by 4. So I have 2 to the power 4, 2 to the power 4, and this is 2 to the power 2. So technically I have 2 to the power 2 plus 4 plus 4. It's basically 2 to the power 10 times 12. This is almost, well, it's exactly the same as the mouse sprite, but it's because the ghost is just smaller. However, a more efficient way is instead of just coding each one of these pixels, which I know it's a bunch of zeros, we're going to just use that palette encoding one. So instead of using 12 bits, okay, which is, instead of saying multiply by 12, I'm going to just multiply it by 2. It's the same amount of pixels. So this one here tells me how many pixels in total do you need. I need 16 by 16, and I have 4 of these images. So 16 times 16 times 4. And this one here is no different. I have 16 by 16 and I have 4 of these images. However, the number of bits I'm coding each one of these pixels now is 2. And now if you calculate the differences between them, you'll see that basically this will be 2 divided by 12, or basically 1/6. So this here is basically just utilizing 16% of the memory that you would have used otherwise if you coded the 12 bits. So that's the main reason why we use encoding. In embedded systems, we don't have a lot of memory, so it's color encoding actually becomes really useful. It also allows me to change these colors on the fly. So that particular circuit here, we can just basically do another circuit afterwards. Let me just move that in here. So for example, instead of that being red, for example, I know that it is some sort of a but I know that it's body, and internally I can change that body color to whatever I want using some sort of an external signal that's coming from here telling me that the body would be well coded using something else, for example. And you can generate these colors on the fly, and that's how we're going to generate them. Okay, so this is these are the two major things that we'll use in the ghost sprite. It's basically movement and animation, and actually changing colors. So let's go back to animation a little bit now, or actually let me show you the palette circuit first. So the palette circuit movement or the palette circuit code that we will see is this is the segment of the total code we're going to be seeing. This is basically the description of the palette that we have, and the circuit that I just described is the following. So that is the output of the RAM. So the RAM again is outputting something that is 2 bits. Okay, so I'm going to take that output in here, and I know it's 2 bits, and I'm going to put it through a lookup table basically, and that lookup table tells me is it 0 0, is it 0 1, or is it 1 0, or is it something else, which is basically just the Y. It's basically just coding that. So if it is a 0 0, I'm mapping it to 0. If it's 0 1 in here like that, I'm just mapping it to this dark gray. If it is other than that, basically in here, which is the Y. However, for the body, what I'm doing is I'm saying, okay, well, if it is a body, instead of just coding it as red, which I could have, I'm just coding it using something else, which is ghost RGB. Where is this coming from? Well, it's the other circuit that I mentioned. So what I'm having in here is this will generate 12. That's basically the palette circuit, but also the palette circuit's going to take another 2 bits coming in here, and these 2 bits will tell me, okay, well, what we need to do is basically some sort of a color in here. That color selector will tell me what color do I want the body to be. If it's red, it will generate that. If it's pink, it will generate this. If it's orange, it will generate that. So technically that will become, actually it's 12 bits in here, and it will take about 2 bits in here as well. So these 2 bits tell me which color, basically body color in here. Okay, so that's basically the palette circuit that we're going to see. So the palette circuit is straightforward. Let's see how the animation is. So in the animation circuit, I'm just focusing on parts of the code that we're going to see shortly, but it's just easier to see it that way. So if we take a look at that, I know that I have 1, 2, 3, and 4. Okay, so the way we're going to be actually accessing that RAM, which is of this size, like we did with the mouse pointer or the generic sprite, we're going to concatenate the XR and YR, and in this particular case now I have them 4 bits each because I have a 16 by 16, so that's the only number of bits I have. I will also concatenate what we call the sprite ID. Okay, so the XR and the YR will be changed based on the frame counter, the X and Y's, and where the sprite is. However, the sprite ID will be basically controlling which one of these. Do I want to display this? Do I want to display this? Do I want to display this or this? And since I have only 4 of them, it's going to be 2 bits. Now, if I want to generate that motion, all I have to do is just generate or move this in a very systematic way. And the way we usually do it is by a counter. So we're going to have an SID counter, which is a sprite ID counter. And again, it's going to be a modulo 2 or 2. Like if you have 5, you're going to need a modulo 5. But in here, it's a modulo 4 since it's 2 bits each, okay? So if you had 5, you would have needed to create something that is modulo 5. So I'm going to create modulo 2 or modulo 4, which is just 2 bits. Okay, and that will actually change automatically at a very specific rate, and that rate is usually 1 over f sprite being the frequency I want to change that, so I create an animation. If I do it very, very fast, it's going to be very fast. I won't see the changes. It has to be slow enough, but fast as well. So I'm going to use approximately 6 hertz. And the way I can do it is basically that I need some sort of a counter to slow down that one or move this one here, and based on the system counter, which is sprite, or I have 100 megahertz, and I'm going to slow it down to 6 hertz, and that's how we did it. However, in the code you're going to see that I'm not going to use a system counter, and the reason why is because I have the frame counter is operating at 60 hertz, which is basically the VGA counter. So instead of moving from 100 megahertz all the way to 6 hertz, what I'm going to do is I'm going to use the 60 hertz frame counter to go to the 6 hertz, which is much easier that way. Okay, and that's what we're going to see in the code. So let's jump to that code that I've been talking about for a while now. So we have in here, okay, so here's the code. Okay, so the code actually, first we're going to start by the RAM, and the RAM is just basically the generic BRAM code. Basically this is the template. This is exactly the same as the mouse pointer. I'm just changing the color depth, basically being from 12 to 2 because it's going to be color encoded, and I'm also loading a different text file in here. So if I take a look at the text file, basically the ghost, the sprite sheet for the ghost, so if you take a look at that, you'll see it's written that way. It's just organized in such a way that it looks, it's just showing it the way that Vivado shows it. It doesn't show it exactly how it's stored. So basically I can't see all the ghosts in here, but you get the idea. Each one of them, even though I'm seeing it, that's in hex. But anyway, so we're gonna go back to the code and we're gonna do that in here. Okay, so that's basically the RAM. So the generation circuit, just instantiate an instance of that RAM, okay, and that's the output of that RAM. So I'm going to read that code, and then I'm going to pass it to my palette circuits, the one that we just saw briefly a couple of seconds ago. And of course, I know that like the generic sprite, like the mouse sprite, I need to utilize or generate the XR and the in region, and that's how we're going to do that. So the pixel generation circuit is just basically that particular code. And now what I have in addition in here, this is the new thing. It's actually, I need an animation timing in here. Well, a new thing in addition to the color. Well, this is how we do the animation. So the animation is done this way. So first you have something we call a frame tick, and the frame tick is based on the X and Y. So when X is 1 and Y is 0, and when X delayed basically by 1 cycle, so the previous X was 0 and the current X is 1. So what this ticks exactly when the major frame counter of the whole the global frame counter basically for the VGA, it's actually moving from 0, 0, 0 to 1, 0. I'm gonna take that because this is actually it will do it at 60 hertz. That's how it will do it. Then I'm gonna take it to a modulo 10 counter because I know I want to move from 60 hertz, as we mentioned briefly, from 60 hertz to 6 hertz. It's basically divided by 10, so I'm going to use it modulo 10. That's basically the C, and because C is modulo 10, if you actually go to the signals, you'll see that C is actually 4 bits, and that's exactly what we saw. It's actually 4 bits. Okay, so that is just a modulo 10, and I'm going to use that C next in here, or C register. That's what I'm going to use with the frame tick to actually say an animation tick, and the animation tick is ticking at 6 hertz, and that's how we do it. So effectively what I have is I have a frame counter that is based on a 100 megahertz that is generating 60 hertz. I took these 60 hertz and I slowed it down by another counter to 6 hertz, and now I have something that ticks at 6 hertz. So whenever I need to do some movement, I can use that particular tick in there. Okay, so I have something that is ticking at 6 hertz. So now we move to the rest. So the rest of the code is telling me, well, the SID which I'm using in here in the address, if it's moving automatically, because this is how we have it, this is auto, it's basically automatically. Well, if it's moving automatically, then you're going to have to go to the animation register. Okay, well, the animation register is just basically a counter that goes from 0, 1, 2, 3, 0, 1, 2, 3. And at what rate? It's actually at exactly the animation tick rate, which is 6 hertz. And that's how we generate it. Other than that, you're actually just going to tell me by some sort of a selector, well, the processor is going to specify whether you want to display this one, this one, this one, or that one. And that's how he's doing it. Again, the core is actually taking the X and Y, and because it has a RAM in it, so it's delaying it by 1. Like the mouse pointer, I'm gonna have to artificially delay it another 1, and that's what you do see in here. So this is an artificial delay because I want basically, here's my core, my circuit or my generation core. It will actually have the XY from the global frame counter. It typically internally takes 1 clock cycles to generate the output, but I'm going to delay it by another 1. So in here I have 2 clock cycle delay at the output, and that's actually that actually conforms with the rest of the or sprite cores, or with the rest of the video cores. Okay, so that was just the pixel generation core. So if I want to actually generate a whole ghost core, I need to actually figure out the wrapping circuit and the blender. And in order for me to figure out a wrapping circuit, I need some sort of a register map. So here's a suggested register map in here. Okay, so the register map is very, very similar to the mouse pointer. So I'm going to split, or the mouse pointer core. So I'm going to split it in half. So the first half is actually specified by the most significant bit to be 0. And then what I'm doing is I'm giving it access to the sprite sheet. So the sprite sheet has 4 bits for the X's, 4 bits for the Y, and 2 bits for the SID, which is the sprite IDE. Okay, it might seem like the mouse pointer because the mouse pointer needed 12. Okay, we needed actually 10, which is 4 and 4 and 2. However, now it's a little bit different because this is for the SID, because the core itself, or the sprite itself, is 16 by 16. But anyway, so the processor can change it if it wanted to. And then the processor also needs to interact with this particular core by writing to its bypass, writing its X0 and Y0 to place it somewhere in there or on the monitor. However, more interestingly is actually whatever we see in here. So what we see in here is a new control register that we did not see in the mouse, and that control register, which I didn't show you in the code, it actually is coming as a 5-bit signal. And that 5-bit signal, we're going to dissect it into 3 things. First, it's actually from 0 to 1. It's basically the ID selector. So the least 2 significant bits, which are here, okay, it's going to tell me if I'm not showing the animation for the ghost, I'm actually showing one of the sprites in the sprite sheet, and I can, since I have 4, I need 2 bits to specify them, and these are here, and that's basically what that control register is doing. Then control 2, which is that one here, is telling me the mode, which is auto. So do I want it to automatically change the SID, or do I want to select them specifically by hand? And that's basically whether I want it to animate or not. That's basically what it'll do. And that's basically the signal, the auto signal that we use in the SID in here. Next, we move into the most significant bits here, 3 or 4, and those are actually just the color for the body color actually. And since I'm using 2 bits, I can specifically just figure out, and these are basically the bits, just basically 4 colors, and I'm gonna just choose red, pink, orange, and cayenne. If I wanted more colors, I just have to add that. So compared to the mouse pointer core, I'll have another input in here, or another register as well, that will allow me to change these. So the processor actually can do that. So we'll take a look at the total code. What it will do is basically it will instantiate a ghost pixel generation, and I'll do basically the wrapping following that particular register map. And it's very, very similar to the mouse pointer. So I have a write enable whenever you want to write to this particular core, and then whether you're writing to RAM or register, and I'm just checking bit number 13. And then if you are writing to a register, which is a control register, you have 4 sub registers basically, whether it's a bypass, the X0 or the Y0 or the control. Okay, and these are based on the least 2 significant bits, like you see in here, these ones in here. Okay, so based on that, I'm actually just writing different data to these particular registers. And of course, at the end in here, it's just basically doing the bypass and the chroma key blending, exactly like the mouse pointer core.